Hello, I'm Jane Berrie. I'm Electronic Design Technology Partner on the ECADStar team here at Zuken Technology Centre, Bristol, and I've been involved in high-speed digital design probably for longer, more years than I care to mention. And today I'm going to talk about the very basics of characteristic impedance and how signals reflect when there's a mismatch. So first I'm going to talk about characteristic impedance, but I'm not going to start with the PCB. I'm going to start with the coaxial cable because it's a little easier to visualize. This is a coaxial cable. It's a 50 ohms characteristic impedance, and so is the connector on the other end. And inside, as you can see here, there's an inner metal core surrounded by an insulator, a dielectric, and beyond that there's a shield, and the signal on the inner core couples from there to the shield, and how it does that controls the characteristic impedance. And of course it's 360 degrees all round, and so is that connector, and that makes for very good matching and impedance control. Indeed, it's a little different from what you get on a printed circuit board. Now, if you want to do basic characteristic impedance calculations on a good old coaxial cable here, well, you can do that pretty well with the formula because it's circles, and circles lend themselves to being treated well by formulas. But on a printed circuit board, the geometries are a lot more complex. There's no surround that goes all the way around with the shield and so on, and because of that you need a field solver, and ECADStar, like other software of its type, has field solvers built into it to solve that problem for you. For example, this is a DDR4 memory layout in ECADStar. From that we can extract an equivalent circuit called a scenario. And if we open one of the tracks in that scenario, we can see its relationship to other tracks and to power and ground planes above and below that control its impedance. It's a track cross-section. From that you can get a field solution, and that field solution can then go on to be used in simulations, so we can see what the waveforms look like, for instance. So I guess you can see that on a PCB the situation is much less controlled than it is in a coaxial cable, or much less easily controlled at least. So if you get imperfections, you get gaps, cutouts and so on in the controlling planes above or below, or both, it will affect the impedance of the signal as it travels along the route. And similarly, you can get interference coming in from the side, and even a grounded track coming in from the side can affect the characteristic impedance on the signal track. The far end termination that's equal to the controlled characteristic impedance of the routing of the signal that goes to it is designed to absorb as much as possible of the energy in the travelling waves of the signals that come along from driver past any receivers and hit that terminator, because you don't want them reflecting back, distorting the signal and so on. And if you encounter an impedance discontinuity some way along, perhaps a difference in trace width or a change of layer, then that causes a partial reflection as well. And if part of the signal goes back, not so much of it continues on. And so the objective is to get the impedance matching as good as it can be. This has been the very, very basics of characteristic impedance and impedance matching. There's a lot more to it than this, but I'll come to that some other time. That's enough for today, I think. So thank you for listening.